Where to go? It's okay. All right.
I spilled some. My bad. It's like on the board. Some is on the
All right. I just managed to get it live just now.
Oh,
Thankfully.
real quick. Would Lions to accept they have memories or not?
Not yet.
No memories, guys.
Only if, of what happened, yes.
Oh. No, you have memories of what just happened. You don't have
Yes.
memories.
Not their own.
You have your own.
Not yet.
Yeah. Remember when you go live and all?
I am. Yeah. Oh, they can.
Are you muted?
No.
Oh. Well, when you start.
They can listen to us talk about D&D. It's fine. Hey fam, they want to hear us talk about D&D. We can.
Yeah, it's always live.
We can do that after the midterm review. Yep. All right.
Why didn't you label? Wait, where is it?
Should be the Phy Geo II Midterm review.
Just call it 253.
Oops.
Keep up the naming convention.
Oops. Fine. All right. We'll get started here in a minute, students. As I just sent out the notification, I will let a few more trickle in. All right.
And Louis just wrote Ram. You go, yes,
All right. Okay. So, for those of you in chat here, give it another minute. I'm really wondering how many students are going to be like, "Hey, that's not my teacher," and just deuces. Like,
I mean, that's what one did on for me.
Yeah.
You know, there, that happened to me. I was sitting there like, wait, this is when you said left.
All right. Okay.
Don't forget to like, comment, and subscribe.
Yes. Like, comment, and subscribe. Okay, here's what we're going to do. I'm going to give it another 2 minutes. Another 2 minutes, and then we're going to get started. All right. Yep, another 2 minutes, and we'll start, and we will field questions and go through the labs.
Hey, and you have 5 watchers.
Yep. If I am not your teacher, don't stress. You might be Dexter's, or you might be Dr. G's. I will still be stepping you through your midterm review, so you can better be prepared. You be better prepared heading in. All right, and it is just about time. Thank you. Yes. Okay, 8:05, we're going to get started. So here's how we're going to structure this. I'm going to step you through each lab that you have done. But what I'm going to do first is, yes, you will be taking the exam online. Yes, you will. You will not have to worry about coming in and seeing our smiling faces. So, all right. So here's how this is going to work. I'm going to field questions about each lab as we start stepping through it. What I would like to do is I would like to start off heading into each section with your questions or things that you have not understood in that lab. Once we have stepped through that, I will give you a very brief rundown of what is in the lab. I will also tell you what is important to know for the midterm. That is probably the greatest benefit of these study sessions, is we are pulling directly from the midterm. I am not going to go through material with you that you don't need to know. So, very important, that part. Okay, so lab one. Lab one, map essentials. Map essentials. All right. So, do you have any questions before I begin about map essentials? I will also give you the chance to ask questions at the end. But, map essentials. Any questions about this lab? Okay. Also, if you are watching this after we have streamed it, what I will do is I will always put what lab we're in as we're doing this, so you can go through the timeline of this as we continue. All right. So, talking about map essentials is basically what you can expect to see on a map. All right. So, in your lab manual, let's get you to turn to page, let's say 5. It's page 5. All right. And page 5, it tells you at the top the essentials of maps. Okay. Those are things you're going to want to know. I would say know a few of them. I believe our question is give us a certain amount. Label off a certain amount of them. But the directional reference, the legend, the source, the date, so on and so forth is a very important thing to see on a map. Very important part of that map. So we're going to go through a little bit of that. So the directional reference the directional reference. The directional reference is going to be like a north arrow or a compass rose. This basically tells you which way is north, not which way is up, that's different. Which way is north, all right, most of the time. Maps that do otherwise are exceptionally rare. Okay. Additionally, moving on from this, you will want the legend or the key. What purpose does that serve? Well, how can we possibly know what the little labeled parts are if we don't have something to tell us? For example, we talked about cities in a state, right? Let's talk about my home state, Pennsylvania. So you could look at a map of Pennsylvania. Maybe you've never been there before. I would use Alabama, but we're all from here. Maybe you've never been to Pennsylvania before. So you would not know the difference between a map label for Philadelphia, Harrisburg, and Pittsburgh. You might just see a little dot telling you the city is there, but you'd see at Harrisburg, which is the state capital, the most common way to denote that is a star with a circle around it. This is what the legend helps you determine. Okay. All right. Additionally, the source. The source is very important. Those of you in my class, we talked about this at length because as we talk about source, it's very important to know the person who is making your map. It is very common for maps to essentially lie to you. It's very easy for a person to manipulate data to show you something on a map, and you look at it and go, wow, that looks fresh and nice. And then you realize that it's basically just trying to skew some of the data. Maybe they will change the colors, maybe they will change the shading. Each one of those can alter the way the map is presented to you. Additionally, the date. The date, also very important. If you're in my class, we talked about how maps that show the spread of the coronavirus or maps that show anything about COVID, the date is immensely important because the information about it changes over time. We find out new things. So the data we present will change over time. So source and date are extremely important. Okay. All right. And the name of the cartographer, the name of the person who did it, is also super important. Again, that ties back into the source. Additionally, you need to know the projection. Listen, those of you who are in my class, you hear me talk about projection at length. I'm not going to go too far into that. But the way a map is projected can make a big difference in the way that the information is presented. A projection can distort a map in a variety of ways. And the projection that you choose is just as important as the information you are displaying. All right. Okay. Next, we're going to talk about something that has two parts here. See it over here. Is a scale. Scale. Okay. So we talk about scale. There are two ways that we have talked about this in class. Is the bar scale. The bar scale. Okay. And a bar scale is a visual representation of distance displayed onto the map. For example, you may see something that looks like a long bar like this that will have numbers, usually starting from 0, or might start from 0 in the center and move outward, and give you an arbitrary number, right? Or you will see ones that are like this, right? So if we color it in a little bit here. These are visual representations of distance. That's what this is, a visual representation of distance. And then we have the RF, which, don't let this bamboozle you, the representative fraction is not a fraction, it's a ratio. It is a ratio. We do not give it as a fraction. Ratios and fractions are oftentimes one and the same and interchangeable, but in this case, on a map, you will usually see, we use 1 to 24,000, so it's pretty popular. All right. you will see one of something to a larger number of something else. And what that means is, you may notice, it has no units. It has no units. One of what? To 24,000 of what? Well, we could look at a map and we could say one, I don't know, marker to 24,000 markers on the map. Basically what this means is any object you use to measure from 1 to 24,000 means that one of those objects, this marker, will be 24,000 of those objects laid end to end on the map. That's what that means. Okay. Additionally, I believe we talked about scale. Talk about scale in general. Scale is kind of a concept that can be difficult to grasp. Those of you who are in my class, you saw that I put up on the TV screen a scale model of the solar system as we move through it at the speed of light, if a pixel was representative of the size of our moon, of the Earth's moon. And we got to see how absolutely immense our solar system is. But what does that mean? Was that map small scale or large scale? What did that tell us? Well, large scale. Large scale means large detail. Large amount of detail. Large amount of detail. Large scale, large amount of detail. So that means that while this globe shows a lot of detail, it doesn't show a large amount of detail. It only shows you states, countries, oceans. You don't get too close, right? Where if we took a map of, here we find one. Oh, here we go. Here's Charlottesville, I think. I don't know. Not sure which Charlottesville that is. All right. This is a small scale map. Why? Because we can see fine detail. All right. I will give you an example of this to help iron this out. So, sorry, I had that backwards. Also, sorry for my handwriting. Let me say this again. Large scale gives you a small amount of detail. Large scale, small amount of detail. That globe does not, it shows you a lot of information, but it does not show you fine detail of that map. A small scale map will show you a large amount of detail. To drive this home, imagine you are sitting at home right now, which I assume you're doing. You're sitting in your dorm, you're sitting in your house, and you look out the window, right? And you see somebody walking by, let's say on the sidewalk very close to your house, okay? So let's say I am like walking down, you can see me very closely, you can say, hey, that dude has glasses and dark hair, and you see a large amount of detail, because you can say, oh, he's wearing a blue shirt, right? Okay? So this is seeing me at a small scale. I won't get too close and scare anybody, okay? But if I back up, and I were to go across the street, and you were to try and look at me from your same seat in the house, but I'm down the street somewhere, you can't make out a lot of detail. You can barely see. You might say, oh, he's wearing a blue shirt. You know, oh no, he's walking. He's walking here, you know? So you have large scale, small amount of detail, right? If I'm walking down the street, you are seeing large scale Mr. K, okay? If I am right outside on the sidewalk, on small scale Mr. K. Yes, thank you. Moving along. All right. Any questions about this? So map anatomy, okay, and scale. Map anatomy and scale. This is what you need to know. Any questions about this? I'm going to stop and give it a minute before I continue on. No? No questions?
No questions.
No questions. All right. I am hoping I explained that clearly enough. All right. So, move on. Lab 2. Lab 2. Topographic maps. Let's see. Where's my model? Here it is. All right, lab 2. Topographic maps. All right. This lab will not be one of those on the midterm that is heavily covered because we don't want to. I don't believe we're giving them a map, are we? One of the big maps. Yeah. Topographic maps I'm going to cover very quickly here. We're actually not going to spend a lot of time on. A topographic map tells you a great deal about the topology of an area. What exists there? Right? What exists there? Topographic maps give you information such as elevation. They also give you topographic. I'm going to start writing this down. So that's very light. Elevation. Landforms. Locations. Lat, long, and degree, minutes, and seconds. These are the things you will need to know for that. I do not think there is a map reading section on there. It is still good to know these in case we ask you a question about this. Still good to know. Are there any questions about topographic maps? I know I really quickly glanced through this, but I do not think there are USPLS ones on there. All right. It converts. Nope, no converting either. All right. Okay. Going to take one more second here. Lab 2, and we're going to move on to lab 3. Okay. Igneous rocks. Before I start, does anybody have anything they'd like me to cover in particular about igneous rocks? Or else I'm just going to go through the majority of what we know. Any questions? All right. Okay. So when we talk about igneous rocks, we have to talk about how they have been formed. Okay? So in my class, what I generally do is before this class, I go out, I buy a soda, I bring it in here, and one of the first things I do is I shake it up and then take off the cap. Now, how does this relate? Well, a volcanic eruption happens because gases build up in the magma and build up to the point that they can no longer contain themselves underneath the layers of rock, underneath the in the magma chamber, and so on. And what happens is those gases need somewhere to go. Those gases need a place to escape to, and that is when you get a volcanic eruption. Okay. So when I take that soda bottle and shake it up and remove the top, and it basically erupts, well, that is a fairly decent simulacrum of what we are talking about. Yes, colors. Okay. Are you talking about the individual textures? Sorry, are you talking about the composition? The composition, like felsic and mafic? Let's see.
You need to memorize the texture composition chart from page 30. Okay.
The answer to that is no. The answer to that is no. You don't need to memorize the chart. What you do need to know is, here, we'll actually segue that into texture, and composition. Okay. So texture, you have 5 things you need to know about texture. Okay? And you need to know the 5 textures. And the 5 textures are the chart is basically a way for you to help visualize how these are laid out and how various rocks fit in. So like a felsic, but aphanitic rock would be like this rhyolite right here. Yep, always a good example for me. Love this one. Okay. Whereas a felsic phaneritic would be like granite. But anyway, let's get on to what those mean. All right. So when it comes to texture, there are 5 things we need to know. Let's start with aphanitic. Aphanitic. So aphanitic, we'll lay this out here. I'm going to choose a different color here so I can keep them separate. We got blue. Okay, let's do brown. All right. Aphanitic means small crystals. Small crystals, okay, which means that it was extrusive. Now, before I go into explaining this, I'm actually going to give you the second one you need to know, and we're going to talk about how they contrast with one another. So the second type is phaneritic. And this means big crystals. And intrusive.
Can you write a little larger?
I will try. Hold on.
It's a little hard to see on the video.
Is it? Yeah, will do.
Just a little.
Will do.
Sorry.
Will do. Oh, you're good. Phaneritic is big crystals and intrusive. Right. So let's compare these two against each other, because these two go hand in hand. All right, so when you have something that is, I'm going to pull up two rocks here. When you have something that is aphanitic, small crystals, which means it cooled extrusively. So here I have a sample of what is called andesite. Andesite has very small crystals in it. You really can't see much detail in the crystals themselves. Okay? And what this means is that this rock cooled extrusively. It cooled very quickly outside the Earth, right? Okay. Inversely, let's look at this sample of diorite right here. This is diorite. So diorite is, well, it's an intermediate rock, but that said, this is phaneritic, big crystals, which means that this cooled inside the Earth, which means that the minerals that make up this rock had time to congeal and come together, and this means that you can see the individual crystals in this rock. Whereas the phaneritic ones, let me actually, aphanitic ones you can't. See the difference here? So one of these is, trying to make sure there it's sharpened. Okay. So aphanitic, phaneritic. Small crystals, big crystals. All right. Okay. So next up is going to be, where'd that go? I want to stay with the book here. Glassy. Okay, when something is glassy, it means that it flash cooled. So here is a sample of dragon glass. Yeah, obsidian, right? This is what happens when lava hits water and very rapidly cools. The individual minerals fuse together and basically create this very shiny, very nice looking rock here. Right. So, flash cooled. All right, next up, porphyritic. Porphyritic. So porphyritic is what happens when a rock says, I'm gonna cool a little bit inside and then I'm gonna cool a little bit outside. So here I have a sample of rhyolite. Let me get as close as I can here. It's a really good sample of this because you can see that there are these little salt and pepper pieces in here, right? You can see like these little black specks, and that is some feldspar in there. But this is what happens when this rock started to cool. This rock started to cool inside the Earth first. But then the volcano was like, nope, it's time, and erupted, and the rest of the rock cooled around those crystals that had already solidified. And you get this porphyritic texture, right? So crystals that exist, larger crystals that exist encased in these smaller crystals, right? Okay. All right, so cooled inside and out. And last but not least, pyroclastic. Pyroclastic. All right. Listen, I try not to laugh. These are pyroclastic means fiery chunks. That's what it means. All right, so let's look at this sample of scoria right here, right? Scoria has an interesting word to describe scoria. It has vesicles, and the vesicles basically mean that air has interacted with this rock to create these interesting patterns that go through the rock, right? Okay. First we have pumice. Pumice right here. Yeah, formed from a nice foamy-like material that can exist on top of lava. Okay. All right. So classic fiery chunks. Okay. So remember, aphanitic, small crystals, extrusive. Maneritic, big crystals, intrusive. Okay? And then you have glassy, which is flash cool. Okay? Porphyritic, which is where it cools inside and out. And then you have pyroclastic, which are fiery chunks of things, which are really dynamic looking rocks that are pretty easily identified to the rest, given their composition and weight and texture. Okay. Here's where we're going to get into the color. We're going to talk about composition. Let's make sure I stay with the book here. At the top of page 28. Talk about composition. So we're going to talk about first felsic. Felsic magmas tend to be lighter in color. Whereas mafic, darker in color. Okay. So what does this mean in terms of composition? So that means that these rocks are fundamentally made of different elements. So let's talk about felsic. For something to be lighter, can that be seen? Yeah, good. I'm just right here on the edge. Okay, so for something to be felsic, lighter in color, which means that that light color comes from the presence of silicates, a high amount of silicates, but a low amount of iron. High amount of silicates, low amount of iron. Inversely, mafic is low amount of silicates, high amount of iron. Okay? Let me show you the difference. Let's bring up my rock here. This is rhyolite, a felsic, a rock formed from felsic magma. It's very light. It tends to be a little bit lighter in weight also. Whereas this is basalt. This is very dark. It's very dense, very heavy. And you can see that they contrast against one another. So lavas that are high in silicates and lavas that are high in iron, ferrous materials. But, of course, as with all things in science, things are never quite that simple. And we get intermediate. Okay. This can be a range. Intermediate tends to be a range. It does not lean too far one way or another. I will again bring up andesite. Andesite. Here is the sample of andesite. So you can see that the andesite is very gray. It's not too light. It's not too dark. It's just very gray. Kind of dull. Right? So it tends to be in a range in between. All right. Do we have any questions about the composition before we move on?
No questions in chat.
All right. So, the chart, I do not believe, oh, hang on.
Would obsidian be an intermediate?
No. Obsidian is very much a very glassy. Usually, obsidian, given its dark color, does come from mafic materials most of the time. Also, obsidian has a little bit of heft to it. So, all right. Okay. So we covered texture, and make sure you know texture, right? And composition. I do not know. Is there identification on the?
I don't have access to it.
Okay. We GTAs have not seen the midterm as of yet. I do not believe that there is rock identification on it. I really actually kind of hope that there isn't. Because I know that that's kind of an imperfect thing. Those of you who have been following along through the videos, I have gotten some feedback that some of the videos are not always clear. It's hard to see. You can't get an idea for the weight of a rock, which also helps quite a bit in identifying it. So I am hoping that is not on there. Right. Okay. Time is it? How we doing? Oh, that's perfect. Yeah. All right. I'm about to move on to lab 3. Anybody have any more questions?
No questions.
All right. All right. So we're gonna along here. Okay. We're going to lab 4. Lab 4. Sedimentary rocks. Okay. So sedimentary rocks are formed through a process. So I'm going to step you through this process, starting with weathering and ending with the formation of a new rock. So when you weather a rock, right? When you weather a rock, happens in 2 ways. 1, chemically. 2, mechanically. Okay, we're going to spend more time talking about mechanical, but we're going to start with chemical. So chemical is what happens when you break a rock down to its ionic bonds. You break a rock down to its baser molecules, right? And usually what happens is water usually is the driver of this, and it creates a solution and usually takes the material farther downstream. It's called a solution load. So you break it down to its ionic bond. All right. Okay. The more complicated one here is mechanical. Mechanical. So when you mechanically break a rock, let's see if I can do this here. I'm going to try and mechanically weather a rock in front of you. Okay, these are some tough rocks. Yeah, so yes, I have mechanically weathered this rock. That is what I have done. You've watched me mechanically weather a rock. All right. It is what happens when a physical process occurs. This is not a chemical process. This is a physical process. Okay. So when mechanical weathering occurs, we measure the size of the clasts, the pieces of rock, in a few different ways. And we're going to talk about, and you will need to know these. Let's choose a different color. Let's see, green maybe? Yeah. Gravels, sands, silts. Gravels, sands, silts, and clays. What I suggest you do, you should know that your GTAs have also taken this class. We teach it, but we also took it when we were undergrads. The way that I did it was I had to memorize gravel, sand, silts, and clays. Gravel, sand, silts, and clays. It is difficult to memorize the particular particle sizes, right? It is not something that is very easy to do because we have the 2 millimeter to 0.05 millimeter and so on and so forth. That is a lot of information to cram into your brain. So what I recommend you to do is if at any point on your midterm you are asked to put these in any kind of order, Gravel, sand, silts, and clays. Every time. Gravel, sand, silts, and clays. This is one of the few things on the midterm that I suggest you kind of drill into your mind. Is gravel, sand, silts, and clays. We'll get to another one, and I'm going to really annoy you guys with the last one. But gravel, sand, silts, and clays. Very important to know. Okay. All right. So it is broken down into individual pieces. I will actually show you a rock that has almost all of these present. So here is this mess of a rock right here. All right. This is a conglomerate. So here is a conglomerate, and you can see that it has various different sizes. So we have gravels. There are some little sand pieces in here, but when you get to look at, give it a side profile, you see that there are much finer pieces in here. There are silts and clays that hold it together and bind it, and basically make it like a glue. Okay. All right. So what happens when you weather a rock? Well, next, you have to transport it. Transport it. Transportation. Transportation. So this is what happens when these pieces of these rocks, whether they be chemically or mechanically weathered, are transported somewhere else. Again, this is usually done through water. The primary driver behind this is water. And you transport them. But once you transport them, you have to find a place for them to hang out and create new rocks. So they get deposited through deposition. Okay. All right. Okay. So when it's deposited, it has a chance to then lithify. The process of lithification. Remember, the word litho, is pertaining to rock. So basically, rockification. That's what you're doing. You're rockifying something. You're making a new rock out of it. Okay? So you weather it. Chemical weathering is breaking it down to its chemical components. Mechanical weathering is breaking it down by piece size, right? Okay, by the size of the particle. Then you transport it. And it's usually done through water. And then it is deposited somewhere, and then it begins to lithify. Okay. When you get to lithification, we have to talk about two things. Choose a different color. Cementation and compaction. Cementation and compaction. So when something is cemented, it means that rock, here I actually pull up that conglomerate again. This rock right here has been cemented together. Well, how do we know this? Because smaller particles have come together and created kind of a glue around the larger pieces of rock, which is what keeps these large pieces of gravel from just falling out of this rock, because they are cemented in there. Okay? Or, inversely, you can compact it. So what that means is over time, you have so much sediment that is deposited somewhere, so much sediment that is deposited, that it will put weight on the layers underneath of it and start to compact it. And over time, that will create a rock all its own. In this, we talk about shale. Shale is one that's very common for this to happen to. Right, so, let's see if there's anything else you need to know on this one. Nope. Just be sure to know that higher energy water can transport larger pieces of material. So basically, the faster the water is, the stronger the velocity, and it will be able to transport larger pieces. Okay. So again, you weather a rock, whether it be chemically or mechanically. Then you transport it. Okay, you move it somewhere else, and that is done through different ways. You get the solution load, or it can just be tumbling down the river. Okay, or then you deposit it. Okay, and you lithify it, and it lithifies in two different ways. It's either cemented or compacted. All right. Any questions on this one?
No question in the chat.
No questions. All right, I'm going to give this just another minute to let this up here. All right, moving on. All right, those of you who have taken my class know that this next one is my favorite. I like this one. All right. This one, we're going to talk about volcanoes. Talk about volcanoes. All right. Do we have any questions before we start about volcanoes? Things you want to be sure that I cover? Give it a second here. Okay. So far, so good. All right. Okay. So the first thing we're going to do is we talk about volcanic eruptions, and again, we talk about gases under pressure. So volcanoes equal gases under pressure. Okay, that is how an eruption occurs. But there are two ways to make a volcano. Well, two ways that we're going to cover. Okay, so
You need to know the 3 types.
perfect. Yes, and I will help you with that.
Of lava.
Oh, of lava. The ahoy hoy, and pillow. Yes, you will, for sure. We'll go over that. Absolutely, I'll be sure to cover that. All right. So when you create a volcano, you can do this in 2 ways. 1, subduction. 2, hotspots. Okay, so let's talk about subduction first. So subduction, if you have a lab manual in front of you, you can see this on page 43. Let's draw a picture together, guys. All right. Okay, we're going to draw a picture. All right, so here's some land. Here's some continental crust right here. Okay, and then we have, let's make some water. Yep, listen, geography is like part art. Which does beg the question why I do this, because I'm not artistic at all. Okay, and then you have a plate. And what happens, and this plate is usually oceanic, so continental, ocean plate. And then what will happen, let me explain how this works. So the oceanic plate will dive under the continental plate. The oceanic plates are typically denser and heavier. And what happens is, because continental crust is lighter and rich in silicates, what will happen is the oceanic plate will slip underneath the lighter plate and dive into the mantle. And as it does so, as it dives into the mantle, the plate will start to melt. The rock will start to melt. And what will happen is that rock, being lighter than the surrounding material, will start to float upward. And I use the word float loosely, but yes, it is kind of like that. And it will create kind of a magma chamber. But because it needs somewhere to go, it will continue to rise upwards and create a volcano. All right. So for subduction, a continental plate and an oceanic plate is the interaction between the two of those. And the oceanic will dive underneath the continental plate and melt and toss the magma upward. Again, this is kind of an oversimplification, but for the terms of this lab, this is what we're doing. Okay, so for hotspots, let me find something here. Take a piece of paper. So let's say you have a plate, right? I'm going to use this piece of paper for the plate. Let's say you have a tectonic plate, okay? And we know that the plates move, right? Okay, so we know that the plates move. But let's say you have magma that wants to rise through the surface. You have a plume of magma coming up from the mantle that wants to rise to the surface. So what will happen is it will rise and it will melt through the plate, And what will happen is it will puncture the plate and create a volcano, right? And what will happen is as that plate continues to move, it'll happen again, right? And it'll continue to move, and it'll happen again. So to give you a real-life analog for this, this is how the Hawaiian Islands were formed. The Hawaiian Islands were formed exactly from this, where what happens is this hot spot of magma rises through the mantle and punches through the crust, and that magma over time creates landforms. And what will happen is the plate will continue to move, and it will happen again, and you will have like these little dots of land all around that plate. Okay? Okay. Okay, so any questions about that before we move forward? Any questions? Okay. All right, so I'm going to erase this because we're going to need more space. Okay. All right. So, talk about 3 types of lava. This was requested, so we're going to go in depth here. So we have the 3 types, right? So we have the we have the pohoi, and we have hello. Something I'm not sure I mentioned, but keep in mind that magma is molten rock that exists underneath the surface, where lava is molten rock that exists above it. Okay, so lava. The lava here, Okay, so high, here's a term I'm going to explain to you here in a second. Viscosity. High viscosity, okay? This also tends to be lower in temperature. Lower in temperature. High viscosity, lower in temperature. Okay, so viscosity is like the ability for a liquid to flow, okay? So what we're going to talk about here is that this has a very high viscosity, therefore it flows slower, it tends to be thicker, but it's also lower in temperature. And we're talking about this relatively, lava is hot regardless. When we say lower in temperature, we're talking like not as many thousands of degrees as something else. Okay. All right, so high viscosity, lower in temperature. Okay. All right. Pahoehoe, on the other hand, is low viscosity, right? High temperature. To give this a real life analog here, if you have something that's got high viscosity, so something that you may experience in your everyday life that is a highly viscous liquid, if you drink cough syrup tends to be highly viscous, right? Where something like water would be low viscosity. It flows very easily, okay? But so high viscosity, high viscosity, lower in temperature. Pahoehoe, low viscosity, higher in temperature. And then we have pillow lava. Pillow lava. Where's that page? I want to make sure I get it. Yep. So typically, it forms underwater. It forms underwater, and it tends to form these strange pillow-looking things, these formations underwater. And it tends to have like a hardened shell. So here, look, and a hardened shell. Okay. So high viscosity, low in temperature. Pahoehoe, low viscosity, high in temperature. Pillow lava is different from these two, where it forms underwater, is a hardened shell. Okay. Any questions about this? Did I explain that effectively?
No questions in chat.
Magnifique. All right. Okay. One last thing to discuss about this. One last thing. Okay. So types of volcanoes. Types of volcanoes. We're going to draw some pictures. If you're in my class, you know that I drew pictures when I talked about this. So we're going to go from cinder cone. Cinder cone. All right. So if I were to ask you to come up to this whiteboard and draw a volcano, right? Well, maybe you would draw some fantastic piece of art, but that's not me. I'm not all about that. What you'd probably do is draw something that looks like this, right? And you start with this bowl here, a little bowl-shaped area here, okay? All right. So a cinder cone is generally characterized by a volcano that has kind of a bowl-shaped part at the top, okay? All right. These tend not to be very high. They don't tend to rise very far up. They tend to be only like maybe 1,000 feet, 1,500 feet. But they also have a central vent. Okay? Central vent. So if we get another color here, CB is going to equal central vent. Central vent. Okay, so it has a central vent for the lava to go. All right, but next we're going to talk about composite volcanoes. Okay, so a composite volcano, let's turn to page 46 here. Composite volcanoes tend to be some of the largest volcanoes. Yes.
You post it after we finish.
The video itself, yes. Yep. You will be able to go back and watch this video afterwards. So, composite volcanoes are usually steep, real steep. Tend to be some of the biggest volcanoes you'll find. Okay. And there it is. So, these tend to have central vent. Okay? Central vent. But you also see places where like lava flows off to the side. You might have some dikes, some vents here on the side, right? Okay? So they have central vent. And then they will have fissures, vents, and dikes that will go through the volcano. Okay. These also tend to be some of the largest volcanoes that we find on the planet Earth. Okay. All right. Some of the most famous volcanoes I think that we know of, the volcanoes we know of by name, tend to be composite volcanoes. Mount St. Helens, Mount Fuji, so on and so forth. And they usually just tend to be these absolutely massive landforms that just, when they do erupt, they generally erupt with gusto. It tends to be very destructive. So, all right. And last, but certainly not least, shield volcanoes. So, my students, I told about the largest volcano in the solar system. The largest volcano in the solar system exists on Mars. It's called Olympus Mons, which means just, giant, really big volcano. Anyway, we go on. So, a shield volcano tends to be very wide. Very wide. Very wide. Like, if I could, let's try to put it off the screen here. Yeah, just like that. See, you can't even tell. There's more. It's more. It goes all the way over here. It's all the way down here. That's right. You can't tell. Okay? But what happens is these lavas, they spring up. And 1 second. And they generally tend to have a large magma chamber underneath. So you'll have this like giant magma chamber that will filter lava through the central vent, but it will do it slowly. It will do it slowly. And what happens over time is these lavas slowly spread out along the outside of the volcano, right? And they will, using this word again, lithify. They will lithify, turn into rock. And then what will happen is the lava will again, until it builds up over and over and over and over and over until you get this absolutely massive volcano. The volcano that I talked about, Olympus Mons, is roughly 70 miles across, and I think 16 miles high, which is ridiculous. So yes, these are the three types of volcanoes. Your cinder cones that are characterized by a bowl-shaped top, okay? They have a central vent and a bowl at the top, right? Where there tends to be like rock and stuff. A composite volcano will be very, very high. These tend to be very high, your most towering volcanoes here on planet Earth. And they have a central vent, but they also tend to have vents, fissures, and dikes on the outside here. And your shield volcanoes. Your shield volcanoes, which slowly build up over time. To give you a real-life analog for this, this is like Mauna Kea, the Hawaiian island. Okay. All right. Are there any questions about volcanoes? Any questions about volcanoes? We have one more to get through, one more lab to get through, and I will try not to. No questions. Perfect. Okay. I'm going to let you guys see this for just one more moment. And we're good to go. Okay. All right. Lab 6. Lab 6, the most recent. Stream discharge. Okay. I'm going to write an equation up on this board. And I told you there are very few things that I needed you to memorize. This is one of them. This is one of them. And I'm going to step you through. Okay. Q equals. I need you to memorize this. I need you to know this string of numbers as you head, this string of letters as you head into the midterm. Okay, so we're going to talk about what these mean. So stream discharge uses something called the continuity equation. And the continuity equation measures the discharge. We use Q because it's quantity, the quantity of water. So discharge, okay? Choose a different color here. Then we have the width. The width. Depth. Okay? And then the velocity. Okay. So discharge equals width times depth times velocity. Okay? All right. I'm going to step you through a question here together.
When is the midterm?
You may want to check when your class is. Yes, whenever your class is when the midterm is. If you're in my class, it's either Monday or Wednesday. If you're in one of the other classes, you're going to want to check. Oh, do be sure, listen, when I've got like 10 of you here, do be sure that you do your midterm the day of. Don't wait. I'm telling you, don't wait. That's bad news. Don't do that. All right. I'm serious, don't wait. Don't miss it. All right. So let's say yes, it is this week. Yes. So that also means that you're not going to see my smiling face this week and not have to hear my voice echoing through this room. You will get to stay home and take your tests from the comfort of your dorm room or your home, and you guys are going to kick ass. I know you will. You guys are going to take it, and you're going to do well. I'm telling you. If you're here watching this, I mean, it's a foregone conclusion. All right. Anyway, let's get back to the last lab here. All right. So I'm actually going to do one of the stream discharge equation or questions with you to step you through it. We are going to use an example on the middle of page 49.
Is this week correct?
Yes. Yes. All right. So let's say a stream has a velocity of 4. Let's see, how far over can I go here? Has a velocity of 4, okay? A width of 5, and a depth 2. It's usually meters or meters per second, but we're just using these variables. I am not going to ask you to convert on this thing. I'm not going to ask you to convert. So what will we do? The first thing I suggest you do when you take this is, first off, have a piece of scratch paper in front of you or something. And write this down. Write the equation down. Put it at the top of the paper. Q equals W times D times V. When you get to a question that has this, you write out the variables. Okay? Make sure you write out what you know. And then plug it in. Plug it in. So we know Q equals 5 times 2 times 4. So you just go across and you get. Oh God, I hope my math was right. I'm a geographer, not a mathematician.
Someone says 40 question mark 3/S.
Hey, that's correct. That's correct. Very good. 40 meters a second. Your discharge. Yep. Okay. Now remember, if you have a question that gives you the discharge, but does not give you one of these, you need to isolate that variable. This is just like balancing an equation. You need to isolate that number by itself, so it doesn't give you the velocity. What you're going to do is you're going to move over, and you're going to take away from the Q and divide by the width and the depth. Okay. Okay? How are we feeling about that? How are we feeling about this?
No questions in chat.
All right. This is one of those things that I would love to hear some feedback from you to be sure you're comfortable with it so that I have covered it well enough.
Aaron says fantastic.
Cool. All right. I don't see any complaints or Mr. King, you've done a terrible job in the chat. That's great. Okay, we're going to move on to the very last part of this. The very last part. And we're going to talk about the storm hydrographs. Again, I don't know if this particular thing will be on the midterm, but we're going to cover it anyway. Okay, so storm hydrograph. So let's take. So you have done this already, so I'm not going to waste your time going through the finer details of this. What I am going to do is cover the one thing that I noticed from the labs that I've graded so far. And one of the things, kind of a piece of wisdom I wanted to impart when you go to do this in the future, it does happen to be in the lab. When you take your data, the most important part of a storm hydrograph, okay, the most important part, and the part that can trip you up from the very start, is you need to be sure that you set up your graph properly. What I mean by that is, one, make sure you label your y and your x-axis properly. So typically, because you are trying to measure the discharge over time, discharge over time. Think of that phrase right there, discharge over time. So it means that what you want to measure in here, you're going to put over the time. So the discharge and time. This is the way I remember it. Discharge over time. That's what you're measuring. Okay? And then what you need to do is you need to look at your graph. And let's say, hold on, I'm going to go look at one that we have here. So on lab 6, you had to measure out these two separate things here, these two separate creeks here. But one thing I noticed is that the discharge chart on this is kind of all over the place, right? So what you need to do is when you look at this, you need to look at the smallest and largest variables on your chart. Before you even start plotting points, look at your smallest and largest variables. So on this one, I believe it's 1287, I think. Yeah, something like that. Like 1287, right? So let me write this down. 1287 is the lowest. But the highest is what? 39, not 4168. All right. One of the things you want to be sure you don't do is don't just take these numbers directly on here and just plug them in. Don't just do that. Don't just take that and plug them in. What you want to do is you want to find a way to properly chart this. So the best way to do that is to find a low number that corresponds or that you can find decent intervals of in between the low and the high. So let's say you went with 1200 to, let's say, 4200. I think a really good way to chart that would be just do it every 200. Right? There are a bunch of lines on the back of these. This was the biggest mistake that I saw on the labs, and I wanted to impart this to the class so that you know that if you have to do one of these on the midterm, you are able. All right. And you're going to do the exact same thing for the discharge of the other, they're both discharged. Well, that's fine. You're going to do that for time also. For time also. Most of these are pretty well segmented, but. And then plot your points. Another thing to mention is when you plot your points, connect the dots. Connect the dots. So if you have, connect the dots. Right? Let's say you have the second creek. Connect the dots. Okay. Any questions about hydrographs? I just wanted to give you a quick tutorial on doing that because I noticed it was one of the things that was the difficulty with the labs. So that is all of the material. Do you have any questions at all for me while I am here? The next time you interact with this class, it will most likely be through the midterm. So if you have anything you would like to ask, now is the time.
There's no questions in chat.
I'm going to give them a minute. I'm going to drink my tea and... No.
When does the storm start and stop? I swear to God, Aaron.
All right. Okay. Well, if that is it, then I appreciate all of you for attending. And if you have any questions, let me know. If you have any labs that you have not done for me, this is for my class in particular, actually for all the other Gs, for Dexter also. Please, please, please turn in the labs you haven't done, please. It does not matter how long ago these labs have been, get them in so that you can get some credit for them, please. It behooves you to do so. It would be so beneficial because, listen, if you're here, I know, if you're attending these things, listen, I know you care about your grades, and I want to see you guys succeed, so please turn them in. All right. That said, good luck on the midterm. And again, do not show up to class. Do not show up to class. Yes?
In the lab, we had to label when the storm started and stopped. How do we do that correctly to make sure we did it well? Okay.
So this is where, again, we get into, you need to look at your time. You need to look at your time, your start and end time, and be sure that you space them out well enough on your intervals on your x-axis. So be sure that you space them out evenly. I think on that chart, they were spaced out pretty evenly by every 3 hours, I believe. But again, just like I talked about the points themselves, find a decent interval for you to plot them. So you can have a nice, neat graph. You will see graphing again in Lab 9 when you do climagraphs. You will see this again. So it definitely is something you want to get used to doing. Okay, I believe that is it. Any other questions? Any other questions at all? I am here to answer them.
No questions in chat so
No
far.
questions in chat. All right, students. Well, best of luck, and I appreciate you attending this. And as ever, if you need anything, send me an email. So, all right. See you later.